This edition of the Bio Report is brought to you by the California Technology Council, providing discounts on products and services essential to every startup. For more information, visit californiatechnology.org/member benefits. I'm Daniel Levine, and this is the Bio Report. There's been much buzz about the microbiome, but what that constitutes can mean different things to different people. Biosortia Pharmaceuticals is focusing on the aquatic microbiome as a rich source of potential first-in-class molecules to address unmet medical needs. We spoke to Ross Youngs, founder and CEO of Biosortia, about what makes the aquatic microbiome compelling as a source of new drugs, how the company goes about mining it for potential compounds, what the company's growing pipeline looks like. Ross, thanks for joining us.
Oh, it's a pleasure to join you. Thank you so much.
We're going to talk about Biosortia Pharmaceuticals, the pipeline of drugs it's building, and why it sees the microbiome as a rich source of natural products that have the potential to create a vast arsenal to address unmet medical needs. I'd like to start with the microbiome itself, though. I think many people have a rather narrow view of the microbiome, often focusing on the colonies of bacteria in the human gut. Broadly speaking, what does the microbiome include?
Well, that's a really good question, and you're right. There is a lot of confusion as far as what that microbiome does include. But essentially, any consortia of microorganisms where they're in concert in a habitat is really a definition of a microbiome. So we hear a lot about the gut microbiome because we've discovered that there's a number of organisms, in fact, quite a different number of organisms that exist within the gut itself of a human. So that's called the human gut microbiome. They've also learned that, for instance, we have a skin microbiome and we have a breast microbiome, and some of the early studies that have come out just recently have shown that there's a difference in the microbiome of a breast cancer patient and a healthy patient. So these microorganisms themselves are not just in consortia in humans, but they exist, quite frankly, across all habitats. One of the richest sources of microbiomes with the greatest diversity, genetic diversity, is the ocean itself, or even any aquatic environment, because there's such a diverse types of habitats that exist, that it's in these areas that all this chemistry of all these microorganisms are at play. And generally, one thing that I would point out is that when you look at culturable microorganisms, you can learn what kind of chemistry they have. But 99% of all microorganisms can't be cultured easily. So therefore, in the microbiome, there's a huge amount of mystery of that chemistry. And I will also give you guys one other fact that's really cool. And that is that 25% plus of all drugs on the shelf today came from that 1% of culturable microorganisms or inspired by the chemistry of those culturable microorganisms. So if we can access the other 99% and access that chemistry right in situ, it should expand the opportunity for new drugs and new cures dramatically based on the evidence.
These organisms are in constant interaction with their environment and play a critical role in human health and disease. Can you give some sense of the types of activity in which they engage?
Well, when you go back to the very first microbiome, which really probably existed on the planet 3.4 billion years ago, the reality of it is all the chemistry of life is directly evolved from those first microorganisms. So it's really, you can count on virtually anything and everything that occurs within a human has its tie back to microorganisms.
Well, the idea of turning to these microorganisms as a source of potential drugs is not new. You mentioned that a large portion of the medicine chest today, in fact, is derived from them. What's been the barrier to really tapping this as a source of medical innovation?
Well, the biggest, let's say, source from the microorganisms themselves has been when you could culture. So as long as you could culture the microorganisms, then you might be able to get at the chemistry. But there's even very good odds you can't get at the chemistry, because just because you can grow it in a culture doesn't mean it's going to elicit the metabolic pathways or the chemistry that is programmed via genetics. So what happens is you put something in culture, the 1% that you can grow in culture, it may not produce a thing. In fact, there's only about a 2% chance that it will produce something that could be interesting. So it's been very tough to get at that. Now, there's been a number of different strategies that are playing out really across the globe. People are trying to come up with strategies to grow and culture these microorganisms under different stresses, in different environments, in different nutrients. And there's some success at being able to expand that. They're starting to look at co-culturing, so you can have the metabolites of one organism interplay with another organism and then potentially elicit metabolites of interest. And you also have the desire to try to culture in situ, but in an isolated or permeable layer type of enclosure where you can get all the nutrients from the environment, but you've got a single microorganism species that's growing in a culture right in that environment. And that's one of the objectives. Then you've got another approach, which is genetic. People are trying to essentially get at the genetics of the microorganism and then look to those genetic codes to insert in other microorganisms. And in that case, the challenge really becomes, do you have all the ingredients you need in order to be able to grow the chemistry or get at the chemistry you're looking for? Because quite frankly, just inserting genes doesn't necessarily give you all those other variables either. And that's one of the challenges. One approach that we're taking, which is really different, is we go right to the aquatic microbiome and harvest the microbiome in the kind of quantity that nobody ever thought was possible. And people have found microbiomes inside of sponges, and then they've been able to harvest the sponges and then study the metabolites directly because they've got enough biomass to do that, or they try to culture. In Biosortia's case, what they're actually doing is they're going to this aquatic environment and harvesting the amount of microbiome that's a little unheard of, hundreds of kilograms of microbiome to start a discovery process.
And what is it about the aquatic biome the aquatic microbiome that gets around this problem of unculturability?
Well, they're already growing in situ. They're already in a consortium of microorganisms, so they are both culturable and unculturable microorganisms having all those interplays. And that right there is one key thing. The other key thing is that the microorganisms in that environment really do a variety of, let's say, things. You may find drug relevant because of inflammation opportunities, oncology opportunities, CNS, neuro opportunities, and then infectious disease. So there is a wide variety of the types of opportunities. And when you go to the ocean, since it was the first microbiome, there's a relevancy to that microbiome and human microbiome. In fact, there's a 73% genetic overlap in the marine microbiome and the human gut microbiome. So it really shows that there's a huge similarity. And since you can't harvest enough gut microbiome to do a direct study, then the marine environment becomes its surrogate.
I understand Biosortia was rooted in the biofuel space initially. How did you come to recognize the opportunity there was to tap what you were doing as a source of new drugs?
Well, essentially what had happened is as we were doing the work in the biofuel space, we certainly came up with a low energy technology for harvesting microorganisms. And that's when we learned that we were really preserving the cells and preserving their metabolites. And we were looking at what we were collecting, and we started to discover that we were really digging deep into the chemistry in a way that we could study that chemistry directly, where we were seeing hundreds of new potential metabolites or secondary metabolites for the chemistry that's the most drug-like chemistry. So it was really that approach that incented us to go down this pathway and pivot. We had to advance our technology substantially, so we put about another $10 million into the technology. And today we're at full scale, fully capable, and have the ability to go to a microbiome in the aquatic environment and recover what would be 1 million grams dry weight of starting material. And then we can study that in order to get right at the chemistry that could be drug-like molecules.
Can you give me some sense of the Biosortia platform? How does it work to find potential therapeutics from the aquatic microbiome? What's the process?
Generally, what we do is we do what we call bottle sampling first. So we'll go to these various environments with scouts, researchers in other regions around the country. They'll take a bottle sample of let's say, a algal bloom. And why we're interested in an algal bloom is that really puts all the other organisms that are in that consortia under stress, and all those metabolites start to really fire. Once we look at that initial chemistry, we kind of fingerprint it and decide, is this a potential site to take our scout vehicle? Now, our scout vehicle is a portable capability to go to a site and do a fairly deep amount of harvest, maybe 50,000 liters, 100,000, maybe even 200,000 liters, in order to be able to get enough starting material to decide, does it justify a full-scale harvest? Now, our full-scale harvest equipment would have the capability of handling 2 million liters in a day. And that's the type of thing that we've done. We've scouted a number of sites. We've done a production recovery at a number of sites. And we even have an upcoming recovery with a scout right at the Scripps Institute of Oceanography, right on their pier that's 100 years old, coming up in the end of the first week of November of this year. The interesting thing about that is you're only at 0.003 grams per liter, and probably our first 4 hours of runtime will provide our researchers with more material that they've ever seen in the microbiome right off the Scripps Pier than that entire 100-year history of the pier.
You've got a growing preclinical pipeline. Can you give me a sense of the types of indications you're looking at and whether you've got any interesting or unusual compounds or proteins that you've identified?
No, we appreciate that. We're highly focused on the small molecule drug-like chemistry. So we really are looking for the kind of things that could hit those high priority unmet needs. So we do have a number of things in oncology, including immuno-oncology, that we're resolving right now, getting confirmation on its hit, because that's a very exciting area. We have found it pretty easy for us to find highly toxic new compounds that have never been studied or never been seen. These are suitable for what's called antibody drug conjugates in oncology, and what we're finding would be that warhead or that chemical that could potentially kill a cancer cell. We've also seen anti-inflammation and IL-17, metabolic areas such as PCSK9, neurological areas such as anticonvulsive. So one of the problems that we have internally is we spent so much time, effort, energy on our actual technology to do this, and now we've just really started to pivot to move our compounds toward INDs. But the late stage approach of discovery with most funding partners is they want to see it at IND in phase 1. And unfortunately, we're not there yet, but we've got a great technology, and now we're focused on moving our compounds to the area where we could do early licensing.
And what's the expectation? How far would you take a compound in the clinic?
Well, generally right now, our major goal is to drive revenue. So for us, we want to get to multiple INDs and license those at the earliest stages. It may change after we become profitable if we decide to spin something off into a new co because it's one of those huge opportunities, or take it into a phase 1. But we really want to focus on being that discovery partner and move things to the point of early licensing. That's where we think our space and our profitability and our long-term profitability will be the highest.
Ross Youngs, founder and CEO of Biosortia. Ross, thanks so much for your time today.
Thank you so much. It's a pleasure.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.